Hello class, this is CSE-4600, Section 1, Week 7, Spring 2025. Alright, new chapter, and that is Chapter 3. We're going to begin our multi-week discussion on memory, starting with a sort of history on how memory has been used to store programs on a computer system. So, a lot of this is a recap of what we talked about in class already, or at least that's what the first half was of this set of slides is about. It's a history of how memory was used to store programs on a computer system. So, if we think of us as programmers, we like our systems to have abundant, cheap, non-volatile memory. Non-volatile meaning if we lose power to our computer system, say we turn off our computer system, any data stored on it isn't lost. This isn't possible, so we have different forms of memory used for different purposes, forming a hierarchy of memory based on speed, size, and cost. So, at the very tippy top of this hierarchy are registers. These are small pieces of memory that can only hold one word of data, 32 bits or 64 bits depending on the architecture, though once upon a time it would have been 16 and 8 bits as well. These registers are the fastest form of memory available to the system. It's also the smallest, and it's also the most expensive, and it's only available on the CPU. We use registers to store things that we want to keep track of, such as the program counter or running values as part of an increment operation. So, registers are only on the CPU. It's not the only form of memory on the CPU, but we'll get to that in a bit. After that is random access memory. So these are the little green sticks that you see jutting out of a computer motherboard. Memory, or I guess I should say random access memory. That is the core subject of what we're going to be talking about. How is memory stored? How is memory used to store our programs on a system? This form of memory is much slower, but it's more abundant. But much like registers, both registers and random access memory are volatile. Once we turn off power to the system, anything stored on it is lost. Secondary storage is slower than that, but it's cheaper and far more abundant. So, if you think about the relative sizes of these things, registers only hold one word worth of data. Random access memory, these days, your typical computer system will have a few gigabytes worth of random access memory available, or a few tens of gigabytes, actually. So that's more common in higher end systems. It's not uncommon to see like 8 and 16 gigabytes being common these days, though some higher end systems will have even more than that, like 32 or 64 gigabytes of memory. And that's because such use cases just require so much memory. Secondary storage is on the order of hundreds of gigabytes and maybe a few terabytes. So 1 terabyte is like 1,000 times more than a gigabyte. Though if we're going by overloading the terms used for powers of 1,000 to mean powers of 1,024, it's not really, but whatever. Anyway, as I said, registers at the top, random access memory in the middle, and secondary storage below that. Though it can get much finer than that. So in between registers and random access memory is cache. The problem with main memory is that the time it takes to access something from random access memory takes several clock cycles, and that means in the time it takes to read something from memory, your CPU could have been doing like several executions. It could have been executing several instructions. So the point of cache is to have a copy of what was from random access memory that is easier to access than if we were to go to random access memory. See, if we need to read something from random access memory, and it takes like several clock cycles for us to even read that data, with cache, if we need to read something from, say, address 1000, well, we'll copy that into cache, but we'll copy everything surrounding it after that. So we copy everything from address 1000, address 1001, address 1002, address from 1000, address 1003, address 1004, address 1005, and so on. You copy a whole block of data from random access memory stored on the cache. The idea is, cache is not as fast as registers, but it's still faster than random access memory. That saves time with reading stuff from memory. This makes your programs run faster because your CPU isn't waiting for data to be read. Well, not waiting as long compared to waiting for random access memory. So cache is an intermediary memory between registers and main memory, or random access memory. And most CPUs will have at least one level of cache. 3 levels is... I would say that 3 levels of cache is the norm. Now, in the past, when we would talk about secondary storage, that just meant hard disk drives. But now we have different forms of secondary storage, mainly non-volatile memory devices. We call them SSDs, solid state drives. The thing about an SSD is that because there are no moving parts, reading stuff from an SSD is far faster than reading from a hard disk drive. They are pricier than hard disk drives, but the storage capacity of your typical NVMe device is about on par with hard disk drives at this point. Although there are some hard disk drives that can go as high as like 8 terabytes, it's not uncommon to see NVMe devices being at least 1 terabyte. So, these days, because of the low power consumption and the no moving parts thing, it's not uncommon to see mobile devices and laptops fulfill all of their secondary storage requirements using nothing but NVMe devices. The reason why we still have hard disk drives is because, well, they're cheaper, and bulk storage for cheap. If you're one of those people who has like terabytes of, like, for example, if you're like a YouTuber and you need to record tons of videos, you want plenty of storage to store, well, all your videos and all your video projects as well. That's why hard disk drives are still relevant, by the way. Below that is removable media, such as, once upon a time, floppy disks. Little circles of magnetic material that you would insert into an A or a B drive. Because once upon a time, the storage requirements, the storage available on your personal computer back then, say like the 1980s and 1990s, hard drives didn't really exist in a way that meant anything. So all of your storage requirements would have been fulfilled using floppy disks. So I put down removable storage. I would add to this tape drives. So these are devices that can hold like tens of terabytes worth of storage, but you don't typically see tape drives apart from archiving stuff in a data center. So this is our memory hierarchy if we were to go a bit finer than that. So if you want some idea on how large these things are, registers can only hold 1 word each. Cache can hold a few tens or maybe a few hundreds of megabytes. Random access memory is a few gigabytes to maybe a few tens of gigabytes. NVMe devices and hard disk drives are about the same. So hundreds of gigabytes to a few terabytes worth of storage. And removable media, well, storage size will vary. Your flash drive for example, could hold maybe a few tens of gigabytes worth of storage, but it's not uncommon to see similar devices that could hold maybe a few terabytes. To me, that's just wild. When I built my first computer, it had a 128 gigabyte SSD, and now I'm up to a 2 terabyte NVMe device. So yeah, I guess that's the wildest thing. NVMe devices are so cheap and reliable that we can now use them as the primary means of storage in some cases. But our discussion here is about random access memory, or main memory as I like to call it, or main memory as it's referred to in other contexts. So really our discussion is, how are we using main memory to store our programs? So the part of the OS that manages memory is the memory manager. This includes allocating and deallocating memory to processes. When we start a program, memory must be allocated to that process. Programs don't become processes until we open them. When we load a program into memory, we need space for that program, of course. So it's the task of the memory manager to make sure that we allocate the appropriate memory for our programs. Once upon a time, when we talk about a memory abstraction for our programs, once upon a time, there was no memory abstraction. When we said something like move register, 1000, that meant move the contents from physical address 1000 to register 1. So when we talk about the memory available to a programmer, it's literally gonna be physical memory. In other words, a programmer would work with physical memory directly. The address range of that is going to be from 0 to whatever the maximum amount of memory was available on the system. And when it came to running multiple programs, well, you just couldn't. It was just not possible to run multiple programs at once. And even if you could somehow run 2 programs at once, the moment that one program would write into the memory space of another, it would crash. So, when it came to that, there were a few ways of storing the user program in relation to where the operating system was in memory. So, one option was to have the OS loaded in the lower part of memory and have your user programs after that. Not really used anymore. This was common in mainframes and microcomputers. The second option is to have the OS in the top part of memory and the user program in the lower part of memory. And the last option is to have the user program in between your device drivers on the top end of memory and the operating system in the lower end of memory. But regardless, you still have the problem of you can only run one program at a time. Once a program has finished running, the OS prompts the user to run another program. Once the new program is entered into the system, that program overwrites the memory that was used by the previous program. We cannot run more than one program at the same time. We can only run one at a time. If we want to run more than one program at a time, we must protect processes from interfering with other processes, but we also need to protect them from the operating system. Threads don't help here because the point of threads is to have parts of a program that can run while other parts are waiting to run. Say one thread wanted to read from the disk, but it's taking some time to read that information from the disk. At the same time, we can if a thread is reading from the disk and it's taking some time, well, we just suspend that thread's operation, put it aside in the meantime, run some other thread instead. This doesn't help because these are threads that are part of the same program. This doesn't help because although running multiple threads helps with the performance of one program? That's the thing. It's for one program. We want to run unrelated programs at the same time. And this is something that the threads abstraction cannot provide. So, we want to run multiple programs on our machines, and these days it's basically a given that your system will run multiple programs. I would go so far as to say it's a requirement. But early systems could not do that. Well, there were a few such systems that can, and that one example is called the IBM 360. This allowed multiple programs to run at once by using specialized hardware to make sure that the memory assigned to one process is only accessed by that process. So, on the IBM 360, memory was divided into 2 kilobyte blocks. Each one is assigned a 4-bit protection key. These keys are held in special registers in the CPU. The program status word of a program contained also a 4-bit key. When a program tries to access something from a specific block of memory, those keys are compared, and if they match, then that process is allowed to access memory. If those keys did not match, it will result to a trap to the OS. That is, it's a trap to the OS where we try to do an illegal memory access. This mechanism protected processes from accessing the memory that is allocated to other processes. And only the OS can change keys. Not only does this prevent processes from accessing other processes' memory, but it also prevents processes from messing with the memory allocated to the operating system. There is a drawback to this, and that is programmers who would write programs for these machines were working with physical memory. So when I say jump 24, that means jump to physical address 24. If I say jump 28, that means jump to physical address 28. If we load two programs where one says jump 24 and the other says jump 28, when we load these programs, one is loaded at the beginning of memory and the second one is loaded after that. Here's the problem. One says jump 24, the other says jump 28. The one that says jump 24, that program starts at address 0. But because we had to load the second program after that, when we have jump 28 in the second program, that program starts at address 16384. Really, if this program were loaded by itself, it would be loaded starting at address 0. So jump 28 would be somewhere within that process's memory space. So if we shift that by 16384 memory spaces, now that jump 28 line is referring to a different process's address space. So that's a problem. We say jump 24 to mean jump to physical address 24. We say jump 28 to mean jump to physical address 28. The moment we move a program somewhere else in memory, those jump instructions don't work anymore. Or well, they do, but the moment you jump, you're in trouble. You're in the address space of another program, you're gonna screw up the other program. Really, the problem is we are using absolute physical addresses, which is a problem when we make these programs to work directly with physical memory. So the moment we shift this program, it's going to screw up the program. And it's also going to screw up whatever other program was loaded into memory. So this is the problem of processes jumping into other processes' memory. We need a means of changing this jump 28. So instead of jumping to address 28, that is a part of a different process's memory space, we jump to address 28 plus wherever the process address space started. So really, this jump 28 should not jump to this 28 here. Jump 28 should actually jump to this compare operation on line 16 at line 16412. This is called static relocation. We need a means of relocating memory addresses so that when we say something like jump 28, we mean jump to the 28th address of the program, not the 28th address in physical memory, because the 28th address of physical memory may be taken up by some other program. Do not jump to physical address 28. Jump to the 28th address in the program. To translate that into a physical address, you need to take this 28 and then add 16384 because that's where our program starts. This is static relocation. It requires that we do an addition operation before we make our jump. Although this mechanism works with preventing processes from accessing other processes' memory, it slows down the program because every time we need to do a memory access, we need to do an addition operation. Needless to say, most modern systems do not do direct addressing of physical memory, with a few exceptions such as with embedded systems. Devices that are designed to only ever run one program, like a thermostat or a camera. Those are the kinds of devices meant for only one program. These are not the kind of devices where you would want to run any program you want, because, well, it literally is not made for that. You would not want to play Doom on a toaster, but I guess that hasn't stopped some people from trying. There's one person who managed to port Doom onto a pregnancy test, but I think that was using the display of a pregnancy test as a output device, so I'm not sure if that counts though. People have ported Doom to run on a camera. I guess a camera is a good example of an embedded system. A camera has software for storing picture information onto a storage device that is probably going to be an SD card. And all the software on the camera is meant for storing images, sorting through images, deleting images. Not meant for running Doom or, well, anything else for that matter. You wouldn't want to play Doom on a toaster. You can't play Doom on a toaster. Because the toaster is designed for making toast out of bread, not for headshotting demons. Anyway, for most computers, or at least for computers in which we want to run multiple programs, if we want to run multiple programs, we ought to be able to relocate memory addresses so that when we say jump 28, we jump to the 28th address for that program, not the 28th physical address. So really, there are two requirements for us to... There are two problems we need to solve if we want a computer system to run multiple programs. The first one we just saw earlier was protect processes from other processes. The other one is relocate memory addresses. Exposing physical memory to processes has several drawbacks. Like, basically, if you allow physical memory to be exposed to a process, it could accidentally write something into the address space for the operating system and basically destroy the system. Lock and key mechanisms. So the IBM 360, so the mechanism that I talked about for the IBM 360, that is a lock and key mechanism. It is a way of making sure processes don't access the memory allocated to other processes, but it does not resolve the relocation issue. It solves one problem, but not the other. We need to solve both problems if we want something that we can use in a general sense. Also, it's difficult to have multiple programs running at the same time, or if there's only one CPU available, it's hard to have them take turns. Again, it's common, I'd say expected, for personal computers, especially, to run multiple programs at once. So, even though we can use a lock and key system, it still does not resolve the fact that we need to relocate memory addresses. So, again, we need to solve two problems: how to protect processes from one another, and how to relocate memory addresses. So, we need something called a memory space. And a memory space is basically the set of addresses a process can use to address memory. So, when I say address space, think of it as like a process's personal space, if you want to think about it like that. Each process has its own personal space in which it can use to lay out instructions to do its work. And we want to make sure every process has its own space in which it can do its work. Each process should have its own space, independent of other processes' address space, except unless they're sharing memory. That's the only exception to this. Every process should have its own address space. Every process should have its own address space that cannot be messed with by other processes, unless they're sharing memory. Think about it like this. In the early days of telephony, people had 4-digit phone numbers, which was enough for connecting like 10,000 people within the local area. What do you think about what happened next? We have up to 10,000 people connected in a local area, but they want to talk to other people in a different area. So to enable communication between these different locales, 4-digit phone numbers were not enough. So you'd group up to 10,000 people in an area, you connect them to a central office. And then you take the next 10,000 people and you connect those people to another central office. And then you take another 10,000 people and group them under another central office. So when you want to dial someone, before you would just dial the 4-digit phone number. But now, if you want to dial someone with phone number 1280, well, here's the problem. Is that Billy or is that Cindy? If I dial the phone number 1280, now we have a problem. Am I calling Billy or am I calling Cindy? We need some means of separating these two phone numbers. And that is what the next 3 digits in your phone number are for. Those are numbers for central offices. So, a phone number, a 7-digit phone number, think about it like this. We dial the first 3 numbers to connect to a central office, and the next 4 numbers after that are to whittle down the possible 10,000 people until we find who we're calling. So if I wanted to call Billy here, I would need to punch in the first 3 numbers. That is the number to the central office. The next 4 numbers after that, that's actually Billy's phone number. If I wanted to call Cindy, I would have to call another central office using the first 3 digits, and then 1280 to call Cindy after that. In a sense, a phone number really is just the last 4 digits. Everything else is just how to get there. And the same principle applies once we get to area codes. So it turns out these 7-digit phone numbers were not enough. We're still not enough. So now we have 10-digit phone numbers. The first 3 digits are an area code. The next 3 digits after that are the number for a central office. So the problem now is there are so many central offices that some of the numbers for the central offices have the same code. So now we need an area code to tell those apart. But the idea is still the same. We have spaces in which we have up to 10,000 phone numbers that we can connect to. If we want to connect to a different set of 10,000 phone numbers, we need to contact a different central office. So Cindy has a phone number of 1280, but Billy also has a phone number of 1280. If you want to call either one without mistaking one for the other, we need to add that 3-digit code that represents a central office. And more to the point, if you want to call from outside this area, we need to add the area code also. Unlike phone numbers, address spaces don't need to be numeric. So the set of web addresses that end in .com, that's an address space. That consists of all the strings that can be made using alphanumeric characters and certain punctuation, followed by .com. So we need to give each program its own address space. So you see these different areas. Think of these areas as different processes. Each one has its own address space. Each one is going to have an address 1280, but it's going to mean different things. So in one area, you're calling Billy, but in the other area, you're calling Cindy. And in the other area, well, there's no one with that phone number. That can happen, by the way. So address 28 in one program will be different from address 28 in another program. Likewise, phone number 1280 may refer to one person in one area, but refer to someone else in another area. So the easiest way to give each process its own address space is to use something called dynamic relocation, where I guess the simplest scheme is to use two registers. The first one is a base register, and the other one is a limit register. The base register contains the address in which the program begins, the starting position of the program. The limit register contains how many addresses that program can address. Basically, the size of the program. Where does this program start? And how large is this program? We load a program into a contiguous space in memory. We load the values for the base and limit register. The base register tells us, once again, where does the program start? And the limit register tells us how large is the program. When we do something like jump 28 in a program, we add the 28 to the value stored in the base register, and then we make our jump. So instead of jumping to address 28, which is incorrect, we jump to address 16412, which is the correct address. Also, what happens is this. When we do our jump 28 here and add it to 16384 to get 16412, another operation occurs where we check whether we are jumping to a valid address. So if we add the value, take our address and add it to the value stored in the base register, first we check whether our relocated address is 16384 or above. But how do we check whether it's within... Okay, so now we've checked the low end of the program. How about the high end of the program? Well, here's what we do. We take our base register, take the value from the base register, add that to the value of the limit register. That should be 32768 in this case. So, if we want to make sure our program is jumping to a valid address, you gotta check whether the address is between addresses 16384 and 32768. So those are the two comparisons that need to be done in addition to that addition operation. So when we say jump 28, two things are happening. First, you add the base register to that address to get your new address, 16412. And then you check to make sure it's greater than or equal to the base register and less than the base register plus the limit register. It's a little bit weird because we start counting at 0, so 16384 really is the first address, and 32768, that's actually the start of the next program. So really you just want to make sure that it's right before 32768, so 32767. So when we do jump 28, we relocate that address to address 16412. We make sure it's greater than or equal to 16384, but also less than the base register plus the limit register, which is 32768. And if it is outside that range, that is an invalid address that would lead to a trap to the OS that is a illegal memory access, and the program would probably segfault or something like that. And this is an easy way of giving processes their own memory spaces because every memory address is generated automatically, and that has the base register contents added to it before being sent to memory. Some systems even protected the two registers so that only the OS could modify them, but not all such systems did. Comparisons, because we need to do two operations, the addition operation and the comparison operation. Those are two extra operations we need to do every time we need to access memory. The comparison is easy, but the addition is slow unless you have special hardware for that. This is yet another scheme that has fallen to disuse. So we no longer expose physical memory to processes, but we no longer use a base and limit register either. So what comes after that? Well, the next thing that comes after that is swapping. So, okay, but to be fair to using the base and limit register, as long as we have enough room in physical memory, we can and do have enough room for all of our processes. But the problem is, there are a lot of processes. A typical system might make something like 100 processes just after booting alone, and that's not to mention all the other programs the user would like to start up. So the issue here is we need room for all of our processes. But if we run out of room for our processes, then we can't run any more processes. Or can we? What if we could just take one of these processes, save the memory contents, put that somewhere safe so we can make room for another process? That is the idea behind swapping. Let's look at how swapping was done originally. When a system starts up, it makes something like 100 processes. So let's just say the OS starts up and it starts up with process A. Over time, new processes are made and they get loaded into whatever space is available. So process B is made, and then process C is made. Process B and C are running at the same time as process A. But let's just say, after some time, process A goes idle. If a process goes idle, it's using memory it isn't using. So, if the memory management system of an operating system is smart enough, it will detect an idle process, and instead of having it hog up memory that it isn't using, we just save that process, we write the contents of its memory into a file, and save it. This frees up memory that we can use to load another process. That's process D here. Eventually, there will be some processes that terminate, and they no longer need that memory. So, once that process is done running, the memory that it had used up is freed up, so now it can be used by other processes. New processes or idle processes that need to run again are loaded into memory. If this was an idle process that was stored on the disk and it needs to run again, because we have the save file, we have a file that contains the memory contents of that process. All we gotta do is read that file and put it back into a free spot in memory. The one weird thing that can happen is, once we have a process that we can swap around, if it goes idle and we put it back, it might be in a whole new location. This is not uncommon. So, over time, if we have a process that goes idle and becomes active a lot over its lifetime, it can move. But the point of swapping moves processes in and out of what is called a backing store. What's the backing store? Well, it's space on the hard disk drive. So, in a way, although our discussion is mainly on main memory, we are talking about, to an extent, the hard disk drive, or secondary storage, insofar that it is used as an extension of main memory. So we use space on the hard disk drive to store idle processes. This makes room available for other processes that need it. We like to think about processes as being fair, but in here, if processes are idle, they're just using up resources that could be used by other processes. Processes don't complain about this. Really, what matters more is that we have space for a process that needs it. So if a process is idle, we can just unload it and load it back at a later time. And processes don't care about that. All they care is that they have space to run. As processes come and go, they leave behind these holes in memory. Although this is not mentioned in the book, it is mentioned in a different book. As processes come and go, it splits apart this area of unused memory into smaller and smaller pieces, and that comes from the fact that processes are just coming and going. This is called external fragmentation, and at the extreme, memory will be fragmented into so many pieces that even though the collective total of that is enough to hold a process, because we have the requirement that processes must be loaded contiguously, that is, no gaps, no cutting, none of that, there might not be a piece large enough to store our entire process. If that happens, we need to resolve that using something called memory compaction, where, have you ever had to defragment a disk? It's the same idea, basically. But basically, if we have our free memory fragmented into lots of little pieces, we use memory compaction to move all the processes onto one end, and then all the free space into the other end. This is a time-consuming operation, however. When a process is created, it's allocated some amount of memory that is determined by the operating system. If the process is fixed in size, that is, it'll never grow, then the OS will allocate the exact memory it needs. No more, no less. But if the process is expected to grow, then it can cause issues if there's no more room to grow. So it's a good idea to, if you know that a process is going to grow, it's a good idea to give it more space than it needs. So when you allocate memory, you allocate it next to a block of unused memory, so that if this process grows, at least it has space to grow into. These blocks of unused spaces, they're called holes. If a process is adjacent to that hole, then it'll just grow into the hole. If a process is in between two other processes, then there's basically no room for it to grow. We gotta move one process out of the way, or we gotta suspend that growing process until there's room available, or at worst, we have to kill the process. When it comes to swapping processes, we only need to swap the parts of memory that are used. It's wasteful to swap the unused portions. Here's another thing. There can be two parts of a program that can grow. The first one is called the stack, and the second one is called the data. The stack is where all your return addresses live. So if you think about how a program works, you have the main function that's first placed on the stack, and there's a return address for that. If within the main function we call another function called function 1, we add that to the stack, and a return address that tells us where to go back to once we've returned from function 1. If we call yet another function from function 1 called function 2, we add that to the stack with that return function that tells us where to go back from function 2 in function 1. So the stack is, in a way, keeping track of where we are in the program based on what function calls we did. If we call a function from within a function, we need a means of getting back. Once the program calls return 0 in the main function, that's the end of the program. So that's the stack. The other one is called the data. That's where all your dynamically allocated memory lives. So when you allocate memory, what we call malloc, for example, space is allocated, and that data segment grows to accommodate our dynamically allocated memory. Some textbooks separate that data segment into two pieces called the heap and the data. So the data segment is where all your constants live. The heap is where your dynamically allocated variables live. But the idea is still the same. We have two parts of a process's memory that can grow: the stack and the heap. And they grow towards one another. If there's no room for these two segments to grow, then we need to move the process somewhere else. We swap out the process until there's room for it to grow, or we have to kill the process. There are two ways to manage free memory. That is a bitmap and a free list. There are two more methods, but those are used by the operating system itself. Those are called the buddy system and slab allocation. Now, we're not going to really talk about that here. We're going to focus more on how free memory is managed for processes, not how free memory is managed for the operating system. So with a bitmap, you divide memory into allocation units. Let's just say that each unit is like 1 kilobyte of memory. So if we make the assumption that 1 unit is 1 kilobyte, then process A takes 5 contiguous kilobytes of memory, and then there's like 3 blocks of free space. Then B takes 6 kilobytes of memory, C takes up 4 kilobytes of memory, and then there's 2 blocks of free space. D is 6 blocks, E is 3 blocks, and there's 3 empty blocks after that. What we want is a means of representing that information. A bitmap tells us which blocks are used. So we use, say, 8-bit words to represent groups of 8 units, whether those units are allocated or not allocated. So take a look at the first 8 bits here. So these 8 bits represent whether that unit of memory is in use or not in use. So 1, 2, 3, 4, 5 kilobytes of use of memory for process A. That means 1, 2, 3, 4, 5 bits are flipped in that order. And then there's 3 blocks of unused space, so that's 0, 0, 0. So this 8-bit word, 1, 1, 1, 1, 1, 0, 0, 0, means 5 contiguous blocks are allocated, and then 3 contiguous blocks are unallocated. The next 8-bit word is 1, 1, 1, 1, 1, 1, 1, 1, and that's because that is representing 1, 2, 3, 4, 5, 6 units allocated to process B, and then 2 units allocated to process C. For process C, there are 2 units of allocated space, then 2 units of allocated space, and then 4 more units of so for the next 8-bit word, it's 2, 2, and 4 units of allocated, unallocated, and allocated space. So hence the bitmap for that is 1, 1, 0, 0, 1, 1, 1, 1. And then for the next 4-bit, and the next 8-bit word is 1, 1, 1, 1, 1, 0, 0, 0. That means 2 units were allocated, and then 3 units, and then 3 units unallocated. So that is a bitmap. So the key thing about a bitmap is we are organizing our bitmap into groups of 8 bits. So every 8 bits represents a block of 8 units, whether those units are allocated or unallocated. The key thing about this scheme here is how big we make our memory units. So when we divide memory into these allocation units, there's a decision for how big we make these units. And it's pretty simple if you think about it. If we allocate large blocks of memory to each process, then that means there are going to be fewer, we're going to have a small amount of blocks to keep track of. That means we need a smaller bitmap. But if we divide our units into smaller and smaller pieces, that means there are going to be more pieces to keep track of. We need more space for our bitmap. What's not mentioned in this book at all is the concept of internal fragmentation. So if a process, so let's say we have a process. Okay, let's say we have a process. That requires 5 kilobytes of memory. And we have memory units that are each 4 kilobytes in size. If we have process A that is 5 kilobytes in size, that means because we are allocating space in 4 kilobyte blocks, that means process A is gonna take up 2 units of memory, where the first unit okay, so let me back up. We divide memory into 4 kilobyte units. And we say process A requires 5 kilobytes of memory. Because we are allocating memory in 4 kilobyte units, when we allocate this memory to process A, it's going to take up 2 units of memory. Even though it's taking up 8, even though we assigned it 8 kilobytes of memory, it only really needs 5 kilobytes of memory. That means one block is going to be completely full, and the next block is going to be partially empty. 75% of it is going to be empty. And that is wasted space. That wasted space is called internal fragmentation. If we instead divided our memory into 2 kilobyte pieces, that means there are more pieces we have to keep track of, but now these units are smaller, so if we allocate memory to our same 5 kilobyte process, we allocate 5 units of memory to process A. That means the first block is going to be filled up, the second block's all going to be filled up, but the third block is going to be partially used up. So that results in less wasted space. Yes, we're still wasting space. We're still wasting 1 kilobyte of space. That is 1 kilobyte worth of space that one process gets to itself without ever using. We mitigate the effects of internal fragmentation by allocating smaller memory units to processes. That comes with the side effect of, well, now we need more space to keep track of all of these memory units. So that is a design consideration when it comes to allocating memory to processes. If we use larger memory units, we need a smaller bitmap. Therefore, if we have larger memory units, there are fewer memory units to keep track of. We need a smaller bitmap. But it can lead to more internal fragmentation. If we have smaller units, that means we have more units to keep track of, but it results in less wasted space resulting from internal fragmentation. This is just something that's just not in the book, but I feel like it's important to talk about anyway. So, it's a balancing act of reducing wasted space and making the bitmap as small as possible. Though there are a few more arguments that would make a bitmap less than ideal, and one such consideration is when you need to allocate memory to a process, you need to find. If you need to allocate memory to a process, say you need k units of memory to be allocated to a process, if you need k units to be allocated to a process, that means you need to find k consecutive zeros in your bitmap. And this is an operation that we must do from start to finish. If we have a large bitmap to represent all our units being allocated or unallocated, that means we have to search the whole thing from beginning to end, finding a sequence of k consecutive zeros representing k consecutive blocks of free memory. This is a slow operation because we have to search the whole thing from beginning to end. That alone is an argument against using bitmaps. So an alternative to using a bitmap is to use a linked list. So, let's read this list again. Let's read this block of memory again. 5 units of memory are allocated to process A. Then, 3 units are unallocated. That's a whole. Then, 6 units are allocated to process B. Then, 4 units are allocated to process C. And then we have 2 units that are a whole. 2 units unallocated. Then we have 6 units allocated to process D. Then 3 units allocated to process E. And then 3 unallocated units. We can just write that down as an entire list, and this is what this part here is. So, the other thing we have to add is the starting address of these processes and wholes. So really what this says is, starting at process, what this says is, the first block is a process that starts at address position 0, and it's 5 units long. The next unit is a whole that starts at position 5 and it's 3 units long. The next item is a process that starts at 8 and it's 6 units long. The next thing is a process that starts at position 14 and it's 4 units long. And then we have a whole that starts at 18 and it's 2 units long. Then we have a process that starts at 20 and it's 6 units long. And then we have another process that starts at 26 and is 3 units long. And then we have a whole that starts at 29 and is 3 units long. So that is a linked list representation that's equivalent to our bitmap here. So here in our linked list, we are sorting our processes and wholes in order based on address. The order in which they appear from start to finish. Regardless of whether that is a process or a whole, we have information on where that segment begins and how large that segment is. So, P05 means process starts at address 0 and is 5 units long. H29.3 means this segment is a whole that starts at position 29 and is 3 units long. There are a few rules to the linked list, by the way. The segments are, as I said, sorted by address, so they appear in order. A segment that is a process will always be adjacent to 2 other segments. Those are either wholes or other processes, or both. This does not apply to a process that's at the lowest or highest ends of memory, because it'll just be adjacent to one other segment. But apart from those edge cases, a segment will always be adjacent to 2 wholes, 1 process and 1 whole, or 2 wholes. Let me back up. A process will always be adjacent to 2 wholes, 1 process and 1 whole, or 2 processes. If a whole is adjacent to another hole. They just combine into one big hole. So we can never have holes adjacent to other holes. They just combine into one big hole. But we can have processes adjacent to holes or processes or some combination of that. So a process can be between two processes, between two holes, or some combination of the two. When a process terminates and leaves behind a hole, if it's adjacent to another hole, they just combine into one big hole. So you can never have holes next to other holes. They'll always combine into a larger hole. Those are the rules for this linked list. Processes are their own thing. If processes will always be adjacent to other processes or other holes, or some combination of the two. Holes can never be adjacent to other holes, they just combine into one. Give me a minute. So, when we have these processes in memory, if we need to load other processes, we need to find a hole in which this new process can squeeze into. So with these processes and holes sorted by address, we can use one of several algorithms to allocate memory for a created process, or another process that is going to be swapped from the disk back into main memory. The first of these algorithms is to find the largest hole just big enough for that process. That is called first fit. Literally, find the first hole that is large enough for a process. A variant of that is called next fit. So, instead of starting over from that position, instead of starting over with our list of holes and finding the first hole that fits, we save our position from the last time we had to search from a hole and start at that point instead. So the location of the hole created by first fit is saved. So the next time we search for a hole, we just start from that previous position, instead of having to start from the very beginning of our list of holes. Another variant is best fit. Find the hole that is just large enough to fit the process. This leaves behind a leftover hole that is as small as possible. The opposite of that is called worst fit. Find the largest hole available to fit the process. This leaves behind a leftover hole that is as large as possible. In terms of performance, simulations show that next fit is slightly worse than first fit. Best fit is slower because it requires searching the list every time a hole is needed. Best fit tends to fill up memory with lots of tiny useless holes. That's external fragmentation. In comparison, first fit creates larger holes on average. All four algorithms, first fit, next fit, best fit, and worst fit, can be sped up by keeping separate lists for processes and holes. For even more performance gains, you can sort the list of holes by size. That makes finding the smallest possible hole or the largest possible hole as easy as looking at the first element in the list. If we sort holes by size, first and best fit are equally fast, and next fit is pointless. The lists for processes and holes are kept in memory, but since the holes are there doing nothing, we can just put the hole information in the hole itself. So instead of allocating memory needed to store information about our holes, it goes in the hole. We put the information regarding a hole in the hole itself, saving up space. Because memory space is precious. We need as much space available to accommodate as many processes as we can. So the lists for processes and holes are kept in memory, but if you want to be smart about it, hole information goes in the hole. So the first hole contains a data structure that contains how many units are in the hole. And then there's a pointer to the next hole, and within that hole, there's hole information that says where is this hole and how large is this hole. And then there's a pointer to the next hole that says, how big is this hole and where does this hole begin? And so on. So we put our linked list in the holes. So we don't waste memory space for hole information as an allocated data structure using up memory. We use the unused memory because once we use up a hole, that's an element in the linked list that we can just remove now. We don't need to store that thing anymore. We can just allocate that entire hole plus the data structure that was previously used for it to our new process. There's also a fifth algorithm that's called quick fit. We sort holes. We keep separate lists for holes by size, commonly requested hole sizes. Finding a hole of a specific size is extremely fast. It's simply checking whether this list of 8 kilobytes holes is empty or not. It has the same disadvantages as all schemes as sort by holes. So quick fit keeps separate lists of holes for commonly requested sizes. So finding a hole of a specific size is extremely fast. Just check whether the list of 8 kilobyte holes is empty or not. Check whether the list for 4 kilobyte holes is empty or not. It has the same disadvantages as all other schemes that sort holes by size. When a process is terminated or swapped out, finding the holes it can merge with can become expensive. If merging does not happen, then we end up with memory fragmenting into smaller and smaller pieces, to the point where no new processes can fit into any hole. And that's external fragmentation. So remember, one of our rules was to merge adjacent holes. If we don't do that, we get external fragmentation. So external fragmentation. So we want to be able to merge our holes so that way, when we need to allocate space for a process, we have a sufficiently sized hole for it. So this is gonna be our last section for this video here. So even with base and limit registers and managing holes, there's still one issue left to resolve. The fact that over time, the size of software has also grown. When this book was made, Windows 8 had just been released. And the memory requirements for Windows 8 are 2 gigabytes of memory. The requirements for Windows 10 aren't too far off. We are at Windows 11 now, and that requires 4 gigabytes of memory. For reference, a 32-bit system can only address 4 billion unique memory addresses, or something like 4 gigabytes of memory. So if you could run Windows 11 on a 32-bit system, you just wouldn't have enough space left for anything else. And the way that Microsoft has resolved this is by making Windows 11 be exclusively a 64-bit OS. Also, as a public service announcement, Windows 10 support ends officially sometime later in the year. So, regardless of the forward trend of operating systems and programs in general requiring more and more memory, we still have the issue of making space for all of these programs, on top of being able to run several programs at once. So, everything that we talked about regarding finding holes for processes, about swapping processes in and out of the backing store, all of that we discussed, it's still not enough. So, how do modern day systems manage all that? Making space for all of our programs, moving processes to and from the backing store, making sure there is enough room for any process we will ever want to run on our systems. How does the system do that? How does it make room for all of these processes? Here's the neat part. You don't. Let me explain. Although swapping allows for multiple programs to run at once, it still has issues. we made the requirement, under swapping, we made the requirement that programs must be loaded into contiguous blocks of memory. They cannot be cut up into pieces. This makes it hard for programs to grow without having to relocate them every time they run out of space. The larger the program, the more time it takes to swap. And the limiting factor here is the transfer rate of the disk. So, what if programs require so much memory and it's hard to swap them the larger they become, and we need space for all of them to be loaded into memory, but it takes more time to swap larger processes? Can't we just cut up the memory into pieces? Well, as a first resort, that's exactly what happened in the 1960s. There were people who would try this out, and this is a system called overlays. When a program started, the first thing to be loaded was an overlay manager, which would then load the first overlay. The next overlay would be loaded into a free space before or after the first overlay, or if there was no room available, it would overwrite the previous overlay. Overlays were stored on the disk, and the overlay manager swapped them between disk and main memory. So, unlike with swapping, where entire programs are swapped, with overlays, we swap parts of the program. The act of swapping was done automatically by the computer, but the act of cutting up programs into pieces, this was a tedious and error-prone task that very few programmers could ever accomplish. So, we have a little bit of a solution here. If we need to make so much space for our programs, we just don't, and we just swap pieces of programs instead. If we can swap pieces of programs, that makes our lives easier. If we can swap not entire programs, but parts of programs, then what happens is we only need, not only does it solve the problem of processes needing more memory as they grow, but if we remove the requirement of processes needing contiguous space, then what can happen is this. If there are parts of a program that don't need to be used, we don't load it. If there are parts of a program that we need to take out because we need to make space for a different program, we can just swap them the same way we did with swapping entire processes, except we're swapping parts of processes. Is this all making sense yet? So if we cut up our processes into pieces, we can swap them as needed. Because these programs are in smaller pieces, they're easier to swap. Because these programs are in pieces, if a process needs to grow, then there is no more requirement for our processes to be in one big piece. We can have one process broken up into multiple pieces, scattered across memory, and it will still work. We don't need the whole program to be loaded into memory either. But the problem is, the act of swapping pieces can be done by the computer, but the act of cutting up programs into pieces is a tedious process. So, what if the computer could just automate that? If we can get the computer to swap pieces of programs, then certainly we can get the computer to cut the program into pieces. That is the idea behind virtual memory, or I guess more specifically, paging. So, here's the basic idea of paging. The memory space of a program is broken up into contiguous pieces called pages. All pages are the same size. Each page maps onto a frame of physical memory. It's the same size as the page. Only the pages a process needs to access are loaded. So a program can run even if it has pieces missing. We only load the pieces that are needed. And that's okay, because in practice, a lot of your programs have special functionalities that you probably don't even touch or you don't even realize exist. Why bother loading those if they're not gonna be used? Ever heard of that meme? I bought X and I'm gonna use the entirety of X where X is some product. It's like that but reverse. Pages that are not used are stored in a backing store. That's usually a space on the hard disk drive. When a program references a page, the necessary mapping is done on the fly using specific hardware. So that relocation is done automatically. So one thing that's not brought up in here is the idea of virtual memory. So basically, every process will think it has the whole computer to itself. If a process starts at virtual address 0, they all begin at virtual address 0. But these pages are going to be loaded somewhere in physical memory. So we need a means of converting that virtual address to a physical address. But that is done by special hardware. So the necessary mapping from virtual address to physical address is done on the fly. If a program tries to access a page that isn't loaded to memory, we get what is called a page fault. That happens because we're trying to read from a page that's missing from memory. When that happens, the operating system is alerted about that, and then it loads the missing page and re-executes the program. So somewhere in the program is a instruction that says read from such and such memory address, but it's on a page that's missing. That results in a page fault. So the operating system loads that missing page, and then it restarts the program by having it re-execute that read instruction. Once that page is loaded into memory, it can proceed as normal. So in a sense, virtual memory is a generalization of using a base and limit register. With virtual memory, instead of having separate relocation for the text and data segments, we map the entire address space into memory units. In a multi-programming system, parts of multiple programs can be loaded into memory at once. If a process encounters a page fault, it can't do anything because there's nothing to do. It has to wait for that missing page to be loaded. This is an operation that can take time because the missing page is loaded on a backing store, that is a space on the hard disk drive. And to read from memory takes longer. To read from memory takes longer than to read from a register. But to read from the disk takes even longer than to read from memory. So instead of just waiting for this process to have the process to have this missing page loaded, we just not run it anymore and run another process in the meantime. Remember back when we were talking about CPU scheduling and how some processes run out of work to do? This is what's happening. When a process encounters a page fault, that means part of its... Okay, so back when we were talking about CPU scheduling, processes can run out of data to process, and the process must stop running because there's nothing else to process. It takes time to read more data from the disk and load it into memory. What can also happen is the process might need to read from some part of its memory that isn't loaded into memory yet. If that happens, in either case, the process stops running because it has nothing else to work on. It has to wait for that other work to be loaded into memory. In the meantime, instead of waiting for this process to load, we take it out from the CPU and run another process in its place. That process waits while another process gets to run. The idea of if we have idle processes, we let some other process run in the meantime. This is how the operating system makes sure that there's always work being done on the system. if parts of a program are missing, we remove that process from the CPU, wait for it to load. In the meantime, we run some other program until that one also page faults. In a sense, we talked about swapping entire processes, but now we're swapping pages of a process. Although it's not mentioned in this book, it is mentioned in a different book. When we talk about swapping these days, we're talking about swapping pages. I guess, put it another way, it's swapping and paging. What we're talking about with virtual memory, what makes virtual memory possible is the use of paging. Cutting up a process's address space into pages, giving it virtual addresses so that we never have to work with physical addresses ever again, and using specialized hardware that turn virtual addresses into physical addresses. I guess we'll have to talk about virtual addresses in a little bit, but I guess that's for next week. Okay, so that's the end of our discussion here. But before we end it off, I do have a short homework assignment for you to do. So, these are just 3 simple problems that you're to do. Pretty basic. The first one is, consider a swapping system in which memory consists of the following holes in order. So there's a 10 megabyte hole, a 4 megabyte hole, a 20 megabyte hole, an 18 megabyte hole, a 7 megabyte hole, a 9 megabyte hole, and 15 megabyte hole. You are to find space for a 12 megabyte hole, and then a 10 megabyte hole, and then a 9 megabyte. No. There's a 10, 4, 20, 18, 7, 9, and 15 megabyte hole in a system. But you need to make space for a 12, 10, and 9 megabyte process. Using first fit, which holes are taken? Using best fit, which holes are taken? Using worst fit, which holes are taken? And using next fit, which holes are taken? So think about it like this. Using first fit is where you find the first hole large enough to hold the process. So I guess I can show you how to solve the first fit issue, the first fit problem here. So we want to make room for a 12 megabyte process, and we have holes that are 10, 4, 20, 18, 7, 9, and 15 megabytes in size. So the 12 megabyte process should go in the first hole that we find that can hold a 12 megabyte process. That's going to be the 20 megabyte hole. That leaves behind an 8 megabyte hole. The next process we need to find a space for is a 10 megabyte process. We need a hole that is at least 10 megabytes in size. And if you go through the list from start to finish, that's literally the first list. That's literally the first hole available. So now our hole is completely filled. So now our list has a 4 megabyte hole, a 20 megabyte hole that is now 8 megabytes because that's where we put our 12 megabyte process, and then an 18 megabyte hole after that. We need space for a 9 megabyte process, so this hole is filled, this hole is filled, this hole is too small. This hole was 20 megabytes, but now it's 8 megabytes because we put our 12 megabyte process in there. After that, it's the 18 megabyte process. Hey, that's big enough. Let's squeeze our 9 megabyte process in there, so that leaves behind a hole of 9 megabytes in size. So that's the answer to first fit. You have to find some way of describing that though. So the 12 megabyte process went into the 12 megabyte process went into the 20 megabyte hole. The 10 megabyte process went into the 10 megabyte hole, and that hole became completely filled up. The 20 megabyte hole became an 8 megabyte hole. And then the 9 megabyte process went into the 18 megabyte hole. So that would be the answer to first fit. You would do the same thing for the other algorithms here, using best fit, worst fit, and then next fit. So that's the answer, but you gotta word it in some way. So that's question number 1. Question number 2 is, in this picture above, you notice how the base and limit registers are the same? Is this a coincidence, or must they always be the same? And number 3, a swapping system takes 4 nanoseconds to read or write a 32-bit memory word. Assuming holes and memory segments are randomly distributed, how long would it take to compact 4 gigabytes of memory? So, basically, How long would this process take, given the following information? It takes 4 nanoseconds to read or write a 32-bit word. There are 4 gigabytes of memory that we have to compact. That means we have to go through all 4 gigabytes of memory because we're assuming that holes and processes are all randomly distributed. So they're basically everywhere. By gigabyte, I don't mean 10 to the 9th power bytes. I mean 2 to the 30th power bytes because we just overloaded gigabyte to mean 2 to the 30th and not 10 to the 9th. And that's confusing. 1 byte is 8 bits. 1 nanosecond is 10 to the negative 9th seconds. And to transfer a single 32-bit word takes 2 operations, 1 read and 1 write. So it would take 8 nanoseconds to move 1 word to a new location. Oh, and by the way, 1 byte is 8 bits. So this is basically a math problem. Well, actually more than that, it's a unit conversion problem. So answering this question requires us to know how to convert our units, but by extension, we gotta know what units we're even talking about. That's why I had to clarify gigabyte meaning 2 to the 30th power bytes, not 10 to the 9th. Again, this is confusing and I wish we had never had to do this, but I have no choice. Apart from saying gib. This unit does exist, but you only see it in like certain other contexts. And this unit exists because 2 to the 30th power is not the same as 10 to the 9th. As much as we like to think that it is not. So yeah, those are your 3 problems for your... Those are your first set of memory problems for Chapter 3. What holes are taken for these 3 processes? Must the base and limit register have the same value, or can they be different values? And how long would it take to compact 4 gigabytes of memory, given all of this information here? So yeah, those are your homework assignments. 3 pretty basic assignments. Just write down your responses to this and submit that on the Canvas. You have about a week to do this, so maybe I'll just make this due on Friday, just so you have a little bit of time, okay? Alright, so I will be getting to grading all your everything else as well, so just be on the lookout for any discrepancies. If there's anything missing from your homework and I say that, hey, there's something missing, let me know about that. If you want to recoup some missing points, let me know and then I'll just recreate it, okay? Okay, that's gonna be it for our first part into Chapter 3. Next week we're gonna talk about paging. Okay? Alright. Have a good one, and I will see you next week. Bye.